Hello students, welcome back to our Engineering Mechanics Dynamics class. In our previous lecture, we studied Newton's second law of motion and we derived equation of motion for rectangular coordinates. Today we're going to extend that equation of motion to cylindrical coordinates and normal tangential coordinates. So in that case, this lecture will be a little bit short. So let's see. So anything that is rotating, for example, the roller coaster, you see it's having a curved path of movement, right? So anything is moving in a circular path that has a center, for example, center of rotation or curvature. You will have a tangential and normal coordinate, and if it's moving in also in z direction, then you can use cylindrical coordinates. We need to know this cylindrical and normal tangential coordinate because some problems are easier if we solve in this coordinate rather than rectangular coordinates. So today's learning objective is formulate equation of motion for normal and tangential coordinates, and then formulate equation of motion for cylindrical coordinates. So like I said, just for example, these bikers are biking in a bank or like a on a path that has a bank in angle. So since they're not on a straight path, they will have a normal and tangential components of their motion. For example, skateboarding. If someone is skateboarding on this curve going this way and coming back, or maybe here coming back, he would have normal and tangential components on for his motion. And also this park amusement park rides, they are moving, rotating, and also so this is moving, right? Actually it will be in opposite direction. It's moving this direction, right? So and they are having normal tangential component, but as soon as the speed goes high, they also move from this direction, so they go high from the ground. So you can use this kind of problem using cylindrical coordinates because it's rotating and also is moving on height. So this kind of problems are easier if we use cylindrical coordinates. And also you see the jet is having a sharp turn. So it's having a turn, and in this case the pilot will feel and the plane will feel the pilot will feel normal and tangential component will have normal and tangential components, and the seat will exert a normal force to the pilot when he is having a curved path instead of a flat a straight line path. So we're going to solve some problems. These are just some examples. It's easier if we use normal tangential component or cylindrical coordinates. So today we're gonna just have the equation. So equation of motion for normal and tangential coordinates. we saw the concept is very simple for the rectangular coordinate. So Newton's law of motion, summation of force equals to mass plus acceleration, which is in vector, and force will be also in vector. So for example, if a particle is moving in a curved path and then it has a center of curvature, right? It will have a normal and tangential component. So for normal tangential coordinate, it's easier because when we have the tangential part component of the motion, so you can have it by this tangent of the direction is moving, so the particle is moving in this direction, right? So the tangential would be tangent on that point, and we'll say summation of force, and then the tangential component ut, and the normal component is always facing towards the center of the curvature. If you remember that, it's very easy to find the direction on a tangential normal coordinate system. So Fn, okay, let me put T, tangential component of the force multiplied by the ut, which is unit vector in tangential direction, and the normal component represented by Fn, n for normal, and then ut is the unit vector in that direction, in normal direction. So if we have that, and if we don't have any binormal force acting on the particle, so meaning there is no vertical force on this plane acting, so the particle is following the curved path only, so we can resolve this force into its components. So it's like the same way for rectangular coordinate we had x, y, and z. We will have a normal component, unit vector normal, plus we'll have a tangential component, unit vector tangent, and mass, and for the acceleration we will have a acceleration normal and acceleration tangent part. So if we solve this equation taking the same unit vectors together, we'll have function of normal force, summation of all the force in normal direction, mass multiplied by normal acceleration, summation of tangential force equal be mass and acceleration in tangential direction. So these are the two equations we're gonna use for normal and tangential coordinate system. One thing to notice is the an, the normal acceleration, can be determined by, if you know the velocity of the particle, whole square by rho. Rho is the radius of curvature, which is this distance, the center of curvature to the particle. So you can get an from there, and at, the tangential component, if you know the magnitude of the velocity, if you take the second derivative, you know that. If you take a second derivative with respect to time, you will get the tangential component of the acceleration. So that's about it for normal and tangential component. We're going to mostly use these two equations and this concept to solve a problem of Newton's second law of motion using tangential and normal coordinate system. Next, we're going to study the cylindrical coordinate system. So we know in cylindrical coordinate we have three coordinate, r, theta, and z. So if we have a coordinate system, we can say this is z, and this is r, and theta is having, this is theta that locates the location of r. And if we have a particle up here, so now we can have the coordinate system, which is can be defined as like z. Actually, let me get rid of this, it will be easier. Z, this is r, so it's defined as the origin. The r is defined by the angle, and once we define the r, then we go up z amount, and then we can get the particle in this coordinate system. So if the particle having a curved path, it can have three components, one in the direction of r, right, one in the direction of r, which I can say fr ur, so unit vector ur, and then the component of the force in r direction. Parallel to this axis here, we'll have summation of f, let me write it down here, summation of f theta u theta, which is this coordinate, this direction, and we will have the vertical one along z direction, which will be summation of f z u z. So u z is the direction, so this will be this upward direction. So this is the coordinate system, and if we apply the same concept that we did for the normal tangential component, so we'll have equation of motion, cylindrical coordinate system. So in here we're again gonna start with we're gonna again start with the summation of force equals to ma, the basic it's in vector form, basic Newton law of motion. And now since it's in cylindrical coordinate, we will have the component of force as r ur plus f theta u theta plus f z u z. It's the same concept that if it was in rectangular coordinate, we would have fx, fy, and fz. In cylindrical coordinate, we are having fr, f theta, and fz. And we will also have the same components for acceleration, ar in ur direction plus a theta in u theta direction plus az in u z direction. And if we solve, so this is the magnitude of the acceleration and this is the direction of the acceleration. So if you combine both sides, taking on this equalizing the same direction components, we will have summation of Fr equals to mass acceleration r summation of F theta, which will be equal to mass acceleration theta, and summation of F z, which will be mass acceleration of z. So these are the equation we're gonna use for cylindrical coordinates. Okay, there is one more thing that we need to add is what if not all the components what if the acceleration is not well defined, meaning you don't have the acceleration component r or a theta or a z, so it's not completely defined. Sometimes you need to do something else to get start using this equation. Some steps need to be taken. So sometimes sometimes you may not have to, but it's just for to know. We can also have tangential and normal forces. We can take the tangential and normal force of this particle to solve or to determine some part that is missing or not given, to start with the equation of the previous slides. So for example, if we have a particle moving which is in radial distance in r, and the particle is moving in this direction, how can we use, so it's in theta, so how can we find additional components to solve the problem? So let's think that the particle has a tangent here. Well, let's assume the tangent here, right? Let's clarify this a little bit. So this is the particle path, this is the particle. The tangent of the particle is this, and it's creating an angle of psi. So it's just to show you that we can take additional steps to find some unknowns to solve the problem. So if this angle is psi, we can use the concept to find this angle, so we can have the normal and tangential components. So this particle we know that there is a tangential component of the particle which is in this direction, and then there is also a normal of the particle which is towards the center of curvature, and this is the tangential component. And if there is any friction, it will be acting opposite to the movement of the particle. So if the particle and tangential component is moving this direction, the friction will be in opposite direction. And assume that there is a force acting on the particle which is P. This is the friction force on opposite, and P, and this is the theta, and this is the r, the length. So we can find the angle psi here, this angle, if we do a little bit of trig. For example, if the particle was here and now it moved to another position up here, right? So the change is this one, which it can be defined d theta. And if we say the curve was like this, the path was this, so we can say this small distance is a straight line and ds, and the change from r, this previous r, to the new position is this small change, which we define dr. So if we have that, and we know the we're looking for the angle psi here, so we know that the this is perpendicular. So this component, you know that any arc can be defined as the change in angle to the length r. So this arc is dr theta, and we know this distance dr here, and then the transverse distance d theta is always perpendicular. We can use this triangle here. This one is not curved anymore, this is just ds, a small segment. We assume it is a straight line because the curve here is very small. So if we take this triangle here, we can use tan psi equals to r d theta. So this arm r d theta over a dr. So what it tells me is, so this triangle we're working on, and we're looking for this angle. So if we use this angle, so the for tan theta we will have this as a height r d theta, and then dr as our denominator, so we'll get our psi, and we can rewrite this as a dr d theta. So if not all the components are given for the cylindrical coordinate, we can use this concept to find some part that can be fed back to the previous slide to solve the problem if needed. But we'll see some equation to if we need to use this equation. Before we stop, let me simplify this triangle here. So draw a big triangle. We're telling that this is dr, right, and this is r d theta, and this is the triangle. So this is the path. This is supposed to be the curved path of the particle, but we take a small distance ds. We assume it's a straight line, and we're looking for this angle psi. Okay, so just to simplify, if we are looking for this angle, we can have this length and this length. So tan theta, tan psi would be, if we take this is as a OAB, so we will be AB OA, right? And then now see AB is equals to same as this length, so we say this is r d theta, and this OA is same as this length because it's a rectangle, so this is dr. And then from here we got r over dr d theta. We just divided the top and bottom part with d theta. So this is how we get 10 psi equals to r dr over d theta. Just to explain it more clearly. Okay, so that was it for today's class. We're gonna solve problem for Newton's second law of motion for rectangular, cylindrical, and tangential coordinates. See you till then. See you. Thank you.